Okay, now we have two cases. Imagine that you have the same dt over dx, the same temperature profile within the same thickness. And here's what happens. K for the copper, for the metals, the conductivity is larger than the K for the plastics. So you would expect the heat flux to be larger for the copper case than the plastic case. So you would say that since, since K copper is larger than K plastic, you would get the heat flux for the copper larger than the magnitude wise. Forget about the minus sign for a moment. The magnitude of the Q copper should be larger than the magnitude of the heat flux from the within the plastic. Okay, so you can have larger heat transfer from the copper. Okay. Well, actually, experimentally, you can observe it in your daily life. Generally, when you touch a metal surface, you're going to feel that it's much colder or hotter than it. Generally, much cold. I mean, if you're touching two surfaces, one is metal table, the other is plastic table or wooden table. If it's cold, then if they're both colder than your finger temperature, you're going to feel that the metal table is going to be colder than, it's going to feel as if it's colder than the wooden table. It's because the heat is transferred much faster on the metal table than the wooden table. It's because the conductivity is large. So that's just an experimental observation. Any question about this? Now, one thing about the minus sign, the reason for the minus sign is the following. Now, tell me what is going to be the dt, or the direction of the dt over dx. For example, if you have a profile like this, let's clarify the minus sign, or let's explain minus sign. Which minus sign I'm talking about? I'm talking about this minus sign. Okay, let's explain it. Now, dt over dx gets a negative value if t is decreasing with x, correct? X. So, like something like this, right? This is x-axis, this is t-axis. Del t over del x, or dt over dx, gets a negative value if t is decreasing. But you should have the q towards the positive direction, plus x direction. To make it to plus x direction, you need to multiply by negative, so that the negative dt over dx gets a positive value, because we want the q to be towards the positive value for temperature decreasing towards the x direction. Okay, that's the meaning of minus. Similarly, dt over dx gets a positive value if t is increasing, correct? Increasing with x. Yes? No? What do you think? Can you hear me?
Yes, Professor.
Okay, good. So if t is increasing with x, dt over dx gets a positive value. but then you should have the flux to go from the hotter temperature to lower temperature. So the flux should be towards the negative x direction. So Q, in this case, Q should be towards the negative x direction. That's why we need to put a negative sign in front of the dt over dx. So minus dt over dx gets a negative value similar to the Q. Okay, that's why. So we want the Q and this. So we want the left and right hand side to be the same sign. That's why we put actually a negative sign there. Any questions so far? Okay. If you don't have any questions, now look at this, what we left here. So we talked about the units, right? But we defined a new quantity called K, and let's define the unit for the K, right? Units of K. So we said that Q is equal to minus K dt over dx. And the Q, we know that has the units of joules per second time meter square or watt per meter square. And that should be identical to the right-hand side, the units of the K times the units of the dt over dx. dt has the units of Kelvin divided by meters, right? By meters, or temperature divided by length units. So the K must have the units of one of the meters cancel, right? And you get the following: joules per second times meter times Kelvin. In other words, this has the units of, if you combine joules and divide by seconds, it's watt per meter Kelvin. Okay, that's the unit for the conductivity. Okay. Good. So, so one last thing I would like to do, I would like to go back to our original system to find temperature profile for steady state conditions. Okay. So let us go back to our original system to find temperature profile for steady state conditions. Okay. Now we're going to learn what's called as a shell balance. We will learn how to do shell balance. This is our system. This side is TH. This side is T low or T cold. Let's call it T cold. Let's be consistent. And here's what we're gonna do. I'm interested in the temperature at any point in the middle, or maybe at some point within the slab. And I'm gonna basically pick a slice, what's called as a shell, a thin shell or a slice at a position x and x plus delta x. This is my x is equal to 0. This is my x is equal to L, right? And I'm curious about how much of heat is getting in and out of this slab or thin slice. And this is, say, the Q at Q in the direction of x. So let's forget about the vector nature of it, and let's say the Q is along the x direction. And this is coming out, it's Qx, but it's calculated at x plus delta x. This one is being calculated at x. Okay. And the shell thickness is delta x, as you see. This is delta x amount. And let's write down the heat balance inside the shell. Let's do heat balance inside the shell. So balance equations are probably one of the most important things that you learn in chemical engineering classes. And we're going to just do very crude balance equation. We're going to write down whatever comes in minus whatever goes out plus whatever is generated is equal to how much it accumulates. Okay. So you say rate of heat in minus rate of heat out plus rate of heat generation Hi, everybody. Can you hear me?
Yes, sir.
Okay, good. Is there any interruption? I just see that it just shows me an icon that it's just waiting.
I didn't have an interruption on my end.
Okay, great. Great to know. Thank you. So is equal to whatever is accumulated. Of thermal energy. Okay. Now this is steady state. So which term is going to be 0? Who wants to tell?
Would it be accumulation?
Exactly. And who's speaking?
Christina.
Christina. Thank you. Yep. That's the accumulation. So it's steady state. Nothing is going to change with time. So there's not going to be any accumulation. Exactly. So we say it's because of the steady state. Steady state means no change with time. And we want to actually do the simplest case where the generation is 0, no generation of heat. Well, basically, the energy is not neither generated nor created, but sometimes you can get one form of energy transforming into another type of energy. For example, you can actually conduct electricity through the wire to generate or turn this electrical energy into heat energy. So we're talking about particularly the heat form of the energy. So you can have like resistors to generate heat, but it's not that you're creating energy from out of vacuum. It's because you're transforming one type of energy to another. So that's not that's not an inconsistency. So you can have heat generation as well. But for this problem, let's do let's solve a simple problem where you don't have any heat generation. So you have rate in, rate out is 0. So rate in is nothing but the flux Qx at x, right? This one is getting in, but times the area, right? So you should multiply it with the cross-sectional area. Let's call it A. And you calculate it at x is equal to x. The reason why I multiply the flux with the A is because I'm interested in not the flux, but I'm interested in how much of heat is being in. So I'm interested in the capital Q. Okay. Minus the heat out is Qx times area, but calculated at x plus delta x. So it's basically this one minus that one, right? And be careful that I'm using plus direction. So this is my plus x direction. So I need to write down my q's towards plus x directions. And it means that if q comes out to be negative, then it's just towards the negative x direction. But when you write it in the equation, generally we write it towards the plus x direction and then let the equation decide whether it's negative or positive. Let the solution decide whether it's positive or negative. So we are just going to pretend as if it's towards the plus x direction. Okay. That's equal to 0. I have no other terms. Now I need to convert it into a differential equation by dividing both sides by delta x. Divide by delta x, and we get qxa at x minus qxa at x plus delta x divided by delta x is equal to 0. And I take the limit, take limit delta x goes to 0. And you have a definition for this. This thing is called the negative of the derivative, right? Because if it were qx plus delta x minus q at x, it would be positive derivative, but this time it's the other way around. So it's the negative derivative of this quantity, which is qxa, is equal to 0. Okay, is that clear?
Yes, sir.
Great. Now, so this quantity, the derivative is 0. So you can also take this area. Area is also constant, right? You know, this is a slab geometry with A constant. A is cross-sectional area, which is constant, due to geometry of this problem. This is a slab, it's not a sphere, so A is constant. Right? So you can take the A out of the derivative and equate it to 0, and then you have this d qx over dx is 0. From here you find that qx is constant because only the derivatives of constants are 0, right? So let's see, we have 15 minutes more, so I want to finish this one. Qx is constant, so can I find, the question is, like, how can I determine t as a function of x using this qx? So the Fourier's law comes to the rescue, because we know that if I know the qx, I can find out the temperature profile, because the q along the x direction is equal to negative k dt over dx, correct? Now I learned in this from this equation that qx is constant. So I'm going to treat this as a constant, and I'm going to solve for the temperature. So you can write down that dt over dx is equal to minus qx over k, and we know that the qx is constant for this problem, as we found, and the k is also, let's take the k constant and take K constant. Okay. And then we need to solve for t. So you rearrange this equation to find dt is equal to minus some constant qx over k constant times dx. And you take the integral of both sides. But since these terms are constants, you can take it out of the integral if you like. And then you find integral dt is equal to minus qx over k integral dx. And you say that at x is equal to 0, my temperature is T hot, right? And at x is equal to x, let me call my temperature as T, any T at x. Okay. And then from here, you find that T minus T hot is equal to minus qx over k, x minus 0, which is x. So you find T is equal to T hot minus qx over kx. But how can we find the qx? How to find qx? We need to, we use, remember we use one boundary condition here. This was boundary condition 1, meaning that at x is equal to 0, t was equal to th. Now I'm going to use another boundary condition, which says that at x is equal to L, t is equal to t cold. So I'm going to place it in this equation to solve for qx. So I find that Tc is equal to T hot minus qx over k times L. Instead of x, I replace L. And then from here, you can find the qx is equal to T hot minus T cold divided by L times K. This result is the heat flux for one-dimensional slab at steady state with no heat generation. And you can actually place this back into this equation to solve for T, and T comes out to be equal to TH minus T hot minus T cold over L times X. Okay. It comes out to be that T came out to be a linear function of X. So it should look like, the temperature profile should look like this. TH, a straight line, T cold. Okay. Can everybody hear me?
Yes, Professor.
Okay, great. Now we solved the question. We found the temperature profile. We found the Q, the heat flux. So are we done? Do you recommend anything we should do before we wrap up with this problem? What do you think? Anything to suggest? Anything we should check? Are we done? Okay, so let me say the following. If you finish solving a problem, you're never done. If you have more time in a test, for example, you should always check your answer. There are a couple of things you should check. For example, for this problem, you can use dimensional analysis to check that the units are consistent, meaning that you have the same units on left and right hand side of the equation. So for example, we found out the Q, right? Let's have a look at this equation. Which units do you have on the left hand side? Let's check. The Q has the units of joules per second meter squared. We asked, is it the same as the right-hand side? The right-hand side has the units of Kelvin for the temperature difference, right? For the K, the heat conductivity, it has the units of joules per second meter Kelvin. Joules per second meter Kelvin. Divided by length has the units of meters. And if you see, Kelvins cancel, and you get the same units, joules per second meter squared. You have the same units on both sides, so that makes sense. So it's always a good idea to check the units whether you get the correct behavior. Let's check the units for this one as well. You have the Kelvin on one side. You have Kelvin minus Kelvin divided by meter times meter. Meters cancel. Kelvin minus Kelvin is Kelvin. So you have the same units on both sides. Okay, so that makes sense too. Another thing you should check is whether that makes the equations make sense. For example, if you increase the x, you see that the temperature decreases because there's a negative sign here, because this is a positive number. This is a negative number. So if you increase the x, you should have the t decreasing. That's the correct behavior. That makes sense, right? Another thing, you should check the sign of this Q. This is positive, right? TH is larger than T cold. So this is positive. So this entire thing is positive. So QX is positive. So QX is towards the plus X direction, and that's correct. Yeah, QX is towards plus X direction. That also makes sense. So you can actually check those things pretty quick to see whether you made any mistake while you derive these equations.